of Statistical Physics. It is really a great pleasure this afternoon to have Jorge Kurchan as a speaker. Probably most of you know him, but I have, as usual, traditionally to say a few words about Jorge. And he got his degree in Buenos Aires in Argentina, and then he has been studying later at Weizmann Institute in Israel and then in Rome. And now he's in Paris since a long time. And he presently is a faculty member of the Laboratoire de Physique Statistique de l'École Normale Supérieure in Paris. And he has been contributing along his life over many aspects of statistical physics, and in particular in out-of-equilibrium systems. And certainly he is very well known, worldwide known, about his very important, relevant contributions about granular matter, spin classes, fluctuation theorems, and many other things that is very hard to list in a few minutes. His large scientific production is probably of inspiration for many people, has been probably of inspiration for many people, not only here, but all over the world. And Jorge, this afternoon, is going to speak about a very nice, at least I want to stress for me, subject that I'm very eager to attend and listen about what he's speaking about. So now it's time to give Jorge space for his seminar, and let me thank him again for his participation.
Grazie, Roberto. Do you see?
Yes, yes.
Okay.
Yes.
Okay. Very good. If you want to ask questions, please interrupt me directly. Okay. So this is work I have, or we are actually still doing with Laura Foini and Silvia Pappalardi. And it's a subject that it mostly comes to us from the field theory people, but I am going to try to convince you that it is a subject that belongs to us, StatMech. So, quantum bounds and Planckian scales. Planckian means that this time, this has the dimensions of time, is what matters. So let me start with an older bound, which has not been proven, so this is still a conjecture, which is the following. If you take the viscosity of a system and you divide it by the entropy density per unit volume, you get this bound, so that the entropy, the viscosity is bigger than something. So let me quickly show you how this can be. So imagine you have hard spheres. Hard spheres, by the way, are automatically Planckian because the only scale there is of time is essentially beta times hbar. So the friction works, the viscosity works because I have these walls and the walls move, and in moving they kick the particles are moving because we are at non-zero temperature, and there is a transfer of transverse momentum from one wall to the other. So now if we go to the limit of zero temperature, then what happens is, as you can see, that when I move the wall, nothing actually is transmitted because apart from a few local rearrangement, nothing is there to take transfer momentum to the other side. The particles are essentially not moving. So the viscosity is zero. Now, what happens if I switch on hbar? So now you know that there is no such thing as non-interacting spheres. Why? Because two spheres, as you know, don't want to be together because, as you know, the wave function doesn't like to be squeezed into narrow regions. This costs you energy. So there is an effective interaction which has to do with a comparison between the de Broglie length and the distance between particles that effective interaction will in effect transmit momentum from one wall to the other. So this effective, let's say, interaction, although nobody has really done this calculation till the end, but you understand that once h bar is different from 0, your viscosity cannot be 0 because of this phenomenon. So this is the meaning of this bound. But the h bar over 4 pi, you would wonder how can one conjecture a 4 pi? And the answer is that there are models coming from field theory of which we expect, or they rather expect, this is Sons, Tarinets, Kovtun, and later Policastro and others, that those models, for reasons that I'm going to come back to, are believed to saturate all of these bounds. So one last reminder, as you know very well, or at least Roberto knows very well, the viscosity is based on a 2-point function that you have to integrate. This is Kubo formula for the viscosity, and the same will be true of all transfer coefficients. Okay, now another bound, this one came later, is the following. You want to define a Lyapunov exponent and try to bound it through quantum mechanics. So one way to do it, sorry, was a question? No.
Yeah,
okay.
No.
One way to do it is quantum and classically. You fire a particle. First, you measure an observable A. You fire a particle until you get to time, a given time. You give it a kick with another operator, and then you fire it back. This is what is called the Loschmidt echo. Because there is chaos, or if there is chaos, this one will come slightly changed, the observable, and if you measure the difference and you do linear response, you discover this quantity, which is playing the role as the Lyapunov separation. So that's one way of introducing it, which is the one I prefer. Or if not, you can introduce the quantity in a different way, which is simply by saying that this thing here, the average of classically of how much A changes when I give it a kick in B, this you can cut at time 0. This is the Poisson bracket squared. You wanted to square it because the signs are random. This grows like an exponential. This would be the normal definition of a Lyapunov exponent written in a slightly bizarre way. But the nice thing of writing it in this way is that then you substitute Poisson bracket by I times a commutator, and you're done. This is the quantum definition you want. And this was made by Larkin and Ovshinnikov many years ago. And the point to remember is that if I develop this commutator, I notice that I get 4 operators, A, B, and all the other combinations. So the Lyapunov exponent so defined is a 4-time function. Okay, so this is what was first done by Larkin and Ovshinnikov, and it was resurrected by Maldacena, Schenker, and Stanford because they wanted to prove a bound to this quantity. And the bound that they proved was this one. So the Lyapunov, as I told you, h bar over t is t over h bar has dimensions of 1 over time, the Planckian time, and this is the bound they proved. Actually, they didn't prove it for this quantity. I will come back to this in a second. They proved it for a regularized version of this one, but it is basically the same idea. The proof is not really very hard, step by step, but when you finish 4 or 5 steps that you have to do, you're a bit lost as to what was the meaning of what you did, or at least that was the case for me. So what you do is you take the correlations and the responses and whatever, and you compute them, or the 4-point function, and you say something about the complex plane of T and imaginary and real, and then you have some analyticity property and some on top of it, properties of analytical functions. I'm not going to go through the proof. You can read it. It's not horribly difficult, but it's not, to my taste, very explicit. So just spoiler, I'm going to describe to you a proof that is quite more intuitive. Okay, so I will need to say this. In fact, this quantity, which is the one that Larkin and Ovshinnikov introduced first, is not ideal because it can be shown that it's a bit messy from the point of view of its definition. There are some of over-leveled energy levels that are not quite clear. So instead of doing this, you take the Gibbs measure, and one strategy is to intersperse the Gibbs measure in this way. So you see, this is almost the same as the first expression, only that there is a beta over 4, beta over 4, beta over 4, beta over 4. So I split in 4 the Gibbs measure. Or I could do another regularization, which we are going to also mention, which is this way, which is nice because it is a commutator, but now you break it into 8 pieces. The important point to make is that these things are bigger than 0, and they are the ones that are going to grow exponentially. It will be necessary for us to say that they are bigger than 0. We are going to use the fact, and they are, because this is a square of an antisymmetric matrix. This is why there is a minus in front, and these are positive quantities. Okay, don't take this too seriously. If you want really to see how to get rid of these regularizations, we can talk about it later. Okay, so what is important about this? That these bounds, conjectured, some of them, the last one, and the first one, sorry, and conjectured and proven the second one, are saturated at very low temperatures by toy models of holography and black holes, which this saturating the bound is something that these people, the people who work on this, consider a symptom of being a model of holography and black holes. Like losing the sense of smell is a symptom of COVID. The saturation of the bound is one of the things that you expect, or they rather expect, from those models. And one model that became very famous because indeed it saturates the bound is this spin glass I wrote to you here. It's just a quantum spin glass, as you will recognize it from many spin glass paper, except that the quantities, instead of being spins, are fermions. And so it's a quantum spin glass with fermionic variables. Now, it was Kitaev who realized that this model had all these symptoms of being like a toy model of holography. As you see, it is very hard to see any black hole in here, but those of you who do spin glasses are accustomed to using models where you don't see the particles. So this shouldn't be a news to you. Okay. It's very nice because unlike the rest of the things they work with this one, you can do everything. So this is a point that is half physics, half sociology. A system that is approaching the bounds I mentioned before is considered interesting for what it insinuates. So if you see this kind of behavior almost in low temperature metals or in quark-gluon plasma, as you do, you may have the suspicion that there is some holography in play at some level, something that has to do a bit with how gravity arises by duality, etc., etc. So this insinuation, if you want, is what makes the bounds popular. But this is a thing that concerns, of course, mostly the people who are practitioners of field theory. But as I will try to convince you, the bounds by themselves are just static. Okay, number 2, brief recapitulation of fluctuation dissipation in the quantum version. So this at this stage has nothing to do with the previous. So you know the fluctuation dissipation theorem, you have a response, and it's the average of the Poisson bracket as I did before. So this is a kick in B at time 0, and this is how much A has changed at time t. Often, please bear this in mind, I will use the integrated version of the response, the primitive function you want. It's for many things a bit easier. Okay, and then the fluctuation dissipation theorem, you have it here. I suppose that you all came across this classical version. And an important thing is that the fluctuation dissipation theorem is not merely a curiosity that says that you can calculate one thing on the basis of another. It is a very important thing. It is at the basis of Einstein's construction for Brownian motion. It is just telling you that if you have a system that I will call thermometer, but it could be a Brownian particle, and I couple it to many copies of a system, of a variable of the system, and what I will see is that these systems are giving me noise through the fluctuations that go in that direction, but they're also, because of the response, giving me friction that takes energy away. And it is precisely the fluctuation dissipation theorem that makes equipartition work, which means to say that the thermometer is reading the correct temperature. So fluctuation dissipation is not just a funny little formula that puts two things in relation. It has to do with energy transfer and thermalization. Of course, the same is true quantum mechanically, but quantum mechanically, maybe some of you have not come across this one. So what you do is, you can prove, is that the correlation is the anti-commutator of these two quantities. The trace, this is the partition function, this is that normalizes this trace. Here you see that if you don't have this factor, this normalization makes the result equal to 1. And you need to do the anti-commutator because A and B, even if they are at the same time, usually don't commute. So you have to make a choice. And the choice is that you will do the anti-commutator, so with a plus. The response instead, and this one is easier to see, you can do the construction and you will see, which is the response to a kick, is obtained, in fact, with the commutator. So this is the same with a minus. And all this is standard. And now I will introduce to you this other function, which we heard sometimes called Whiteman function. It's neither this one nor the other one. It's a third one that for us will be very important, but it hasn't, you won't find it a lot in books. But for us, it's going to be important. How do you obtain it? You split the Gibbs measure in two, and then you write it ordered this way. In fact, you can order it this way or the other because of the cyclic property of the trace, it gives the same result. This quantity, I'm going to call it perhaps Whiteman function, or perhaps this midway function, or simply F. Okay, it will be important for us. It can be related, and a part of my talk will be about that, with the other two. And again, for the response, I will often use the integrated version because it's better. Okay.
Jorge?
Yes?
Can I ask, what is F classically?
It boils back to the correlation.
Okay.
So these two commute, and it just falls back to a correlation. So classically, it becomes nothing special, just a correlation. Okay. I can tell you quickly what F is, but I will skip that. If you have questions, maybe I'll go back. I mean, one interpretation. Now, the fluctuation dissipation theorem, which is a relation between response and correlation, you have it here. This is the quantum version. It's very, very easy to prove. I'm not going to do it, but it's really one line. And this is the relation that it holds. And you see that if h bar is small, then you develop the tangent to first order, the hbar goes away and you're back in Fourier space to the usual fluctuation dissipation because omega gives you a derivative. But, and this will be important for us, you can do it in two steps. You can relate C to F and then F to R. And if you eliminate F, you get the usual one. But for us, this one is going to be the most interesting, these two. So now you have operators, for example, the one that takes you straight from R all the way to C is the operator that multiplies in Fourier space by the hyperbolic tangent. But we will need the intermediate ones because these are the ones that are going to be most interesting. Let me already tell you why this is nice to use these two steps. The reason is that you see that hyperbolic cosine and hyperbolic sine are analytic, while the tangent is not. So in all the complex plane, they are entire functions, and this is very helpful. Okay, so you can take the bus in two steps and do a correspondence in the middle, or you can use directly this one. So this is in Fourier space. What about time domain? Well, in the time domain, it's nice because now these intermediate steps can be easily written like this. The cosine of the derivative means that you're going to do the series, the Taylor series of the derivative as if the derivative would be a number. So it's going to be derivative to the nth power divided by factorial and so on. And these two formulas are the ones that allow you to go from F outwards. They are these two, to C and to R. And then we will see how to invert them. Okay, and now very easily, if you have a function that was exponential, then C, applying this operator, C captures a factor cosine, and now it's with the exponent inside, and R captures the factor with the exponent. And now, in that case, if the function was an exponential, you could easily eliminate F, and you will see that C and R are related via a tangent. But now this is in time domain. Okay, time domain is very, very rarely used for fluctuation dissipation at the quantum level. Although in the classical one, it's the most common thing to use, but not the most common, but very common thing to use. And we are going to be interested in functions that have exponentially decreasing or exponentially increasing parts. And because this is defined for certain windows like this, Fourier is not very good. So because Fourier lends itself very badly to using windows in time domain. So for us, having things in time is going to be nice. And let me repeat again, if the function is an exponential, then when you apply fluctuation dissipation, what you get is just a cosine and a sine of the exponential coming out. It's a particularly simple thing because when you apply the sine of the derivatives, hyperbolic sine of the derivative to these things, you resum the series and you get these two results. Okay, and now let us consider the inverses. So these are taking us back. These are the ones that are going to be important for us. The inverse is after a little bit of work, but not too much. You discover that to go to F from C, so it would be this one, what you need to do is to do a convolution between C in time and this orange object. So omega here and always is going to be our inverse Planckian time. So you see what happens. The hyperbolic cosine, so I will go on to the next one so that you see it better. The hyperbolic cosine here squared and here linear are bell-like shapes, and what fluctuation dissipation does in these formulas is that you have your, for example, in this case, psi, which is the integrated response, and you convolute it with this bell-shaped curve. Remember again, omega is the Planckian time. And so this Planckian time goes to 0 in the classical limit, and you see that you are convoluting with a delta function. And you get the usual fluctuation dissipation relations that are the classical ones. There is no derivative because I use psi, which is the integral. So, morals of all this. Fluctuation dissipation in time is more complicated, but when you look at it in quantum mechanics, it amounts to a differential operator that is a bit bizarre, or a convolution with a function whose width grows with h bar, and it becomes a delta function in the classical limit. So already you see that quantum mechanically correlations and responses are the same, but you are seeing them through the wrong glasses. They are blurred. That is what quantum mechanics does to these objects. Up to here, we don't see much physics in this, so we will see later. So why is fluctuation dissipation related to the bounds? Question, no. So in order to take the Maldacena-Schenker Stanford bound, you need terms that come from commutators and have 4 operators. This is why they are called out-of-time order correlators. People talk about OTOC or OTOCs. This is not nice because although you can write fluctuation dissipation for 4-point function, it's not the ones we prefer. There is a trick to convert these things into 2-point functions, which is the following. You write the matrix element of what you want to do, and then you say, okay, let me consider this sandwich coming from one space and this sandwich coming from another space. So you duplicate your Hilbert space, and you can, in this double Hilbert space, which is duplicated this way, you can rewrite this thing as a 2-point function, but now in another space, where the P operator just swaps the 1 space and the 2 space. The Hamiltonian is just the sum of the same Hamiltonian acting on one and acting on the other. The A thing is the operator living in both spaces, and the B the same. You're not probably going to be able to follow the detail, but believe me, this is a trick whereby you have converted a 4-point object, a 4-time object, if you want, into a 2-point object. And then, because you feel encouraged that you have a 2-point object, you define a correlation, a response, and an F, the mid one, just as you did before, exactly as you do in general. You do it because you want to. At this stage, there is no justification. And then you develop these things, and you discover that the correlation and the F function have a piece that is exactly the regularized pieces I showed you before. So by miracle, what you have now is that these guys are exactly the ones that give you the Lyapunov exponent. And moreover, these guys, you can show that with time, they go to 0 rather fast, so they don't count. So now, the quantities that matter for us are encoded in this correlation and this response that are complicated ways in which we took 4-point functions and we made them 2. And of course, these 2 terms are positive. I said it before, but I say it again. You can see that it has squares all the way. They grow exponentially. This is the Ehrenfest time. It doesn't matter. It's a constant. But they grow with a Lyapunov. And now, lo and behold, we have this relation, which is the quantum fluctuation dissipation, as I presented it a while ago. But we know that the pieces that matter to us are positive. So necessarily, this cosine has to be positive. And this already tells you that there is a bound, that the Lyapunov cannot be any value, because otherwise the cosine will have the wrong sign. So to recap what I have said up to now, with a tiny rewriting that, by the way, is very standard in the field of quantum physics, to convert this 4-point into a 2-point function, and then applying the ordinary fluctuation dissipation, we immediately get the bound. Because otherwise, the cosine makes a mismatch in the signs of these two, and that's not nice. And that's contradictory. And in fact, what happens is that the cosine is positive throughout this regime. As you go down in temperature, this quantity changes, it grows, but if it hits this line, it will hit the contradiction I mentioned before. And so the poor system is obliged to do something like this to respect the bound and not enter contradictions. Okay, but the point I want to make, and that is important, the calculations, you can check them in about half an hour, but what is the important point is that now the proof is perhaps not especially shorter, it's more or less of the same length as the original one, but now it makes clear one thing, which is that we only use to prove it fluctuation dissipation plus the positivity of 2 functions. So fluctuation dissipation gives you a contradiction because it makes two different, when you violate the bound, it makes two positive functions have opposite signs. So what you say immediately is, okay, but this is what I have to look into now. It would seem, this is a strong suggestion, that if you are going to look at the bounds, you better try to look, the clue you tend to have is that the main actor here is fluctuation dissipation. So this is the road, after having observed this is the road we have been taken. It's not complete, I'm just going to give you some hint, but I present this as a cultural appropriation. We are appropriating for StatMech things that were more considered to belong to the realm of field theory. So first thing, let's talk about general correlations and responses. Remember that the transport coefficients, which as you know very well are integrals of 2-point functions, current correlation, we don't have yet a bound, a strict bound. So we would like to know what are the bounds, the quantum bounds of that are satisfied, that are obeyed by correlations and responses. And one first immediate answer is there cannot be a bound, for one simple reason, that if you have a response and it satisfies that the imaginary part, this is true classical and quantum mechanically, and if it satisfies that omega times the imaginary part of omega in Fourier space, then essentially it's okay. This is the second principle. This is the work you do at if you force your system with frequency omega. Other than that, essentially there are no conditions. And how do I prove that there are no conditions? Very easy. I just pile up a lot of fermions or bosons, oscillators, calculate the response, but I choose their frequencies so that they are distributed in this way. So I take a family of oscillators whose distribution of frequencies is P of omega. The only thing it has to have is to be bigger than 0 because it's a probability. But because this is related to this, then the condition of the second principle is automatically satisfied, but I have no other condition except for silly things of integrability of P of omega. So this means that I can do whatever. I can construct for you, if by choosing P of omega and suitable oscillators or fermions, I can build for you the response you want, provided that you want this one, that satisfies this one. So don't expect something very general as a bound, because I can do whatever. So this is an argument that is already not good. However, I'm going to describe for you a basic mechanism, but as you would expect, given what I've just said, it requires extra hypotheses, because without hypotheses, you can do whatever. We have not yet worked out what are the good hypotheses, the most economical ones, or the best ones to do bounds for transport. The game now, in our view, is to find the good hypothesis, not to be able to prove anything. Because you know that you're not going to be able to prove anything, but you have to know what is the good question to ask. So let us go back to the fluctuation-dissipation theorem. Worked one of the formulas. Remember that it was a convolution that you see here. This is one of the transformations. And remember that you're convoluting with a gray thing. The gray thing is this gray thing. And also remember that this becomes a delta in the classical case and has a width omega. This is omega. And now imagine that your function, for example, is exponentially decreasing as so, like so. Now you're convoluting with this thing. Now, in the classical limit, no problem. The convolution of an exponential that is decreasing with a delta is itself. But now begin to turn on h bar, and you will get something that essentially keeps the exponent the same, until you get to the point where the exponent here, where this exponent a, becomes the same as 2 omega. Remember that 2 omega is the Planckian level. And there a catastrophe happens. Not only this is no longer a delta, but it's a disaster, because this curve here and this curve here, this one doesn't fall fast enough, so that in the end, when you look at this piece of the integral, it is clear that what will dominate is this part. So suddenly, when you get to this point, you get a transition in all your formulas. And instead of being more or less a convolution with something that is like a kind of delta out of focus, now instead of being a delta out of focus, when h bar crosses that level, you get a completely different sort of behavior where what dominates is the shortest times. But these shortest times are not usually given to you, because when people usually give you the asymptotic regime, but they don't give you what happens at the very short times. So now everything depends upon details. And this is what is happening in the extreme quantum regime, where your exponent is falling much faster or faster than the Planckian exponent. The same happens with a growing function. With a growing function, what you see is that this decrease and this increase is too violent if you are beyond the bound. And so that instead of region around here dominates, what dominates is the distant future. So these are long times for people who do quantum chaos. This is the Ehrenfest time. So now we have a transition from this region dominating to times that usually are too long and of which we know really very little. So already we see that fluctuation dissipation has a lot to say about what happens with exponents that grow or fall with rates that are comparable to the Planckian scale. So conclusion is that as soon as your exponent, be there positive or negative, but in absolute value, begin to be comparable to the Planckian scale, it is not the same with a response or a correlation, because one is twice the other, but there is a dramatic behavior in how the way that fluctuation dissipation treats your functions. And all the dependence, when you do this transformation, either goes to the short times, the collisional times, or to the post-Ehrenfestian times, which are the long times. Okay. So let us take an example of something that decays exponentially. So imagine I have a response, which is the derivative of psi, by construction, psi is a primitive, that goes exponentially. And let us suppose that it's falling too fast, faster than the Planckian scale. When I calculate this, well, you can do it, and I'm doing concretely what I said in words here. So I calculate this and I get this sum, and you already see the phenomenon I was saying. This term has the exponent that the original response had. But now this one, because this A is larger than 2 omega, this one already wins because it has a smallest exponent. And it wins in front of this one and so on. So at the end of the day, what happens is that if this number, the coefficient, is non-zero, what is going to dominate is the Planckian scale, and your original exponent is gone. So when you calculate f, your exponent that you supposed you had in the response has disappeared, and the one that has appeared is precisely the Planckian scale. But you need that this coefficient be non-zero. And we don't know that. This has to be an assumption. As I said before, because everything is possible, you cannot prove that this is non-zero. So this cannot be proven. You have to somehow use some extra assumption to argue for it. And now that you calculated the famous f from this formula, you immediately can calculate the correlation. And again, you conclude that if this is non-zero, the correlation now is falling slower than the response and is satisfying a bound. It is falling at the Planckian scale. So what happened? You tried to make a system whose response was very violent, falling faster than Planckian, but the correlation does not follow and it goes at exactly the Planckian scale. So we get a bound for the correlation, and in the same way you can get a bound for the response with the inverse formula, but you need to do this assumption that a certain coefficient is non-zero, and this we don't know how to prove, but you cannot prove it, because it's easy to construct an example with the famous oscillators I mentioned before that violates this. Okay, so what we argued is that a kind of argument of stochastic stability. We said, okay, we have this thing which we would like it to be non-zero. Imagine it is zero. So now let me perturb a bit the system by some means, for example, coupling my system to certain oscillators. Then generically the response is going to change in very arbitrary ways, and this will kick this result from being exactly zero to being non-zero. And it's a kind of argument of stochastic stability or codimension, in the sense that like when you do level repulsion for quantum systems, it's not a proof that two levels cannot cross. You simply say that almost any perturbation will make the crossing be avoided. Here it would be an argument of this kind. But we need to work more on it, because what is a generic perturbation? What is the normal thing to ask in a physical system? Are physical perturbation always going to be like this? We don't know. At this stage, we cannot say. But bear in mind that if you don't argue some way like this one, or maybe some other way, there's no general theorem that you can prove. Okay, let me go back to transport for a second. So transport, usually I mean, at least in this domain, viscosity is the popular one. Let me do as if it were transport of energy because it's easier, but the idea is the same. So you have a conductance, which plays the role of the viscosity, but here it's a heat conductance. We assume that the system has a decent conductance, so that more or less leaves out 99% of the one-dimensional model. But in 3 dimensions, this is quite usual, the Fourier law. So you have a finite conductance of the system. And of course, the definition of having a finite conductance is precisely that you have this equation that has a name which I forget. Oh, the Fourier, I suppose, heat law.
Yeah.
Okay. And in Fourier space, as you know, this reads like this. So you have an exponent here. And now imagine that we had bounded exponents. We had said that under certain conditions, when you have a decreasing function that decreases like e to the minus something to a times t, this exponent was bounded. So, so this means a bound here, which means that k cannot be as large as I want, because, and k being as large as I want means that I'm doing distances that are as short as I want. So if the Fourier law would be true for any short distance, then I would be able to violate the exponential bounds, even for a normal system. But if this were, so there is a characteristic length shorter than which I can, if the bounds that I have been discussing for the decrease, exponential decrease, are valid, below this length, quantum mechanics doesn't allow you to have a decent Fourier law. That's what these things are saying. So there is some quantum effect at short distance, and the bigger h bar is, the shorter, the longer this distance, at which these bounds tell you don't expect to have this law because you won't be able to have it. Don't expect to have this kind of law because you won't be able to have it, because then in time the decrease is going to be too fast and it will violate the Planckian bound. So this already tells you something about the lengths that you can afford to have. And it tells you something about the physics of a presumable bound. But as I say, all this is tentative, and we haven't been able, and nobody has been able, to really prove a bound for transport. Let me say in passing that bounds for transport are much more interesting than a bound for a Lyapunov. A Lyapunov is, after all, a very exotic object, which very rarely is useful for anything. A transport coefficient is a real thing. So if you are more or less concretely minded, those are the bounds you would like to prove, and those are the ones you do not have. Okay, is there a bound for transport, meaning that transport coefficients have to be bigger than something from the quantum point of view? And if so, under which assumptions? What exactly do you have to put in to prove that this is so? This is still an open question, much researched question. If you want, our clue about this is to say fluctuation dissipation is where you have to start to discover who is the culprit of this situation. I would say start with fluctuation dissipation. This is our feeling at this time. However, by its own, it won't be enough. You need to suppose something else, because as I told you, this brings otherwise counterexamples. And why are we so happy about fluctuation dissipation entering this game? For field theorists, fluctuation dissipation is nothing. It's just an exotic equality that interests some other people. But for us in StatMech or in thermodynamics, it's very important because it's something that has directly to do with how a system responds to what you do to it and how it changes heat. So for us, it's good news. As I was saying before, it allows us to culturally appropriate part of this subject for us. So thank you very much.
Thank you, Jorge.
Can you see me now?
Yes. No, not for the moment. I see other people, but not you.
Not me. Okay. I have to stop sharing if I find where was the thing.
Yeah.
Stop presenting. Okay, now I should have stopped presenting. Can you see me now?
No, I see Christian.
Not yet, Jorge.
And now? No.
Not
Oh, wait. Now?
Now,
Yes.
Good.
Okay.
Good. Okay.
Well, Paola want to ask you a question, please.
Yeah, so I wanted to ask you that, I mean, it's just a very naive question. Does the bound on the transport coefficient just come from the fact that the equation you wrote is not valid at any length scale? I mean, just that
yes. The question is, how does the length at which it stops being valid grow with hbar and decreasing temperature? So yes, of course.
Okay. So it's basically your question is like, what is the length scale which I find hydrodynamics, basically?
Exactly, that's exactly the question. And at this length scale, this I suppose everybody knows it, but I didn't. This length scale goes to infinity as hbar goes, as t goes to 0 and hbar is finite. Mm-hmm. So you cannot have a length that is when hbar becomes very when the temperature becomes very low and hbar is big, let's say, you cannot have the k you want and still have thermodynamics. And still have ordinary hydrodynamics. Or to say it in another words, hydrodynamics, the way we know it, is always classical, which is something we also expect.
Mm-hmm.
Well, this is, just a comment. There are no questions for the moment. This is really consistent. I mean, this seems very plausible. I must admit that all your argument is really solid, despite you stress many times that there are no real proofs of these statements, but it looks really reasonable. So I'm wondering is, I think that one could have in mind also some the possibility of having some measurement or verifications of that. I think considering some special model and trying to find out if there is a regime where actually you observe that you depart from a standard hydrodynamics.
Probably, and I guess that if you ask people who work with chains, there's extensive work which I don't really know, but Paola can say, or Andrea can probably say, there must be tons of things on that direction. I don't know. I'm not really good for that, and those are things that should be okay, because in the computer it's shortish lengths you want, and it's big values of hbar you want, but that you can get for very easily inside the computer. So I guess that this must be.
You can check it in principle.
Yes, I suppose that, and so I guess it must have been checked. That thermodynamic. I don't know how developed is the physics of transport at small scales in a deeply quantum system. This I don't know. I suspect that all this Fourier law breaks down and something happens. But I guess that maybe people know this, because I'm not an expert.
I don't know, but hopefully there is someone who knows.
Yes.
Sorry, if there are other questions, please go ahead.
So maybe if there is no other question, just a clarification on the question I was asking before. So basically, I mean, because also classic. I mean, I was just thinking to a classical picture. To be honest, before. I mean, just saying that also classically, I mean, hydrodynamics is defined at some larger scale, and so this doesn't really make sense in defining somehow transport coefficients below that scale, right?
Sure. So the scale that you can, the coarse graining scale that you can allow yourself to use, goes to infinity as the temperature goes to 0 with hbar finite. So what do you call a long enough coarse graining? I agree with you. I agree with you. By construction.
But then the question would be: so the bound that you are looking for is a bound that just comes from the system being quantum, or just from the fact that hydrodynamics, let's say, needs like a minimal length.
No, I think it comes from being quantum, because if you make the Planckian time become very long by just picking the parameters, you can make the coarse graining you have to do more serious, because then you're essentially, it's as if let me put it this way. When you say that you want to coarse grain, you say you want to coarse grain with respect to the lattice size, for example, no? Which would be reason, or to the particles distance between two particles. What I would say is that quantum mechanics gives you an extra scale, which could be in an extreme quantum case longer than that, and that you cannot go beyond that scale in an extreme quantum case.
Okay. So yeah, that was exactly, this was my question. So in general, I would expect that this bound is like, at least from your example in hydrodynamics, it will give you a smaller scale than the what I would call the classical one that you need for doing hydrodynamics.
Exactly.
But in an extreme case, okay, I see.
In an extreme case, then even at many particle distances. And this, you see, if the de Broglie length in a gas is much longer than the interparticle distance, well, things happen, no? Typically it becomes superfluid or whatever. But if it didn't, then you wouldn't be able to do hydrodynamics of that. This is what I.
Okay.
But then it makes a transition, so I don't know. But yes, maybe you can find an example that does.
No. Okay. Thank you.
So I have a question remark as well.
Who's I?
Giacomo.
Yes.
So if I understood well, you took these quantum bounds of Lyapunov exponent from the field theoretic context, where they took the smallest time related to Lyapunov exponent and say this has a lower bound due to quantum correlation in the very essence. So you say, okay, but Lyapunov exponents are not that physically relevant. I want to look at correlation and responses, and I find that as well I have a bound on the shortest times for correlation due to quantum correlation.
Some bound, but above all, we can rephrase their proof, rewrite it in a language in which it becomes a property of usual correlation.
Okay, very good. So what you have, your argument is general with respect to the presence or not of quantum chaos. So it might apply even to quantum system without quantum chaos, or is related to quantum chaos.
So if you are, this is something that we have discussed a lot, because there is a more or less a consensus that you don't have a Lyapunov in most physical cases. So quantum spin chains, nobody expects them to have a Lyapunov exponent. But they are in some sort of sense chaotic in general, no? If they're not integrable, because, well, they have other properties like they can thermalize and things like that. What do you have a bound for that? And the answer is, in principle, no. There isn't any bound that I know of that applies to something whose Lyapunov is 0 or something. However, can you say something more? Well, what we were trying to do with this blurring and fluctuation dissipation is to try to see if we get something a bit more robust than just a bound on a Lyapunov. The blurring is something that is there always. So we think, but there's a lot of work to do, and it's all very tentative at this stage. But we think that, yes, that maybe one can find things that are true and that don't require you to invoke a Lyapunov exponent.
Okay, thank you.
Jorge, sorry, I have a curiosity, a technical point that probably is not of much interest for many other people. But tell me, if I understood correctly, the function that points out the real essence of this bound is the function f of t, as you showed to us. It comes out from a sort of, how to say, you stressed several times the technical trick to go from a 4-point to a 2-point correlation function. Why this function has this peculiarity? I mean, it seems to be much more relevant because if I understood correctly, if you consider just the correlation function, you don't really realize directly the role of this bound. While f points out naturally. Why? There is a reason for that.
So I cannot say exactly, but it's called Whiteman, and I think Whiteman was somebody who was doing a rigorous field theory or something like that. But we met a situation like this with Laura Foini when we were trying to do ETH, so eigenvector thermalization hypothesis, and there it was super clear that the F made life infinitely easier for you. So technically already everything was 1,000 times easier. So it would seem that this function is the one you have to use. I don't know, it's kind of a more natural quantity. Yeah, and it's surely going to appear a lot more, I'm sure, because of especially the work of these people, but it appears everywhere, and it's much, much easier to work with it and standing there to move to the other ones, and not vice versa.
Okay, thank you. Other questions? Comments? Well, we see Andrea, who is probably saying something.
Bye.
No, he already knows everything.
Of course.
Lucky man. So, okay.
But you know, I've been always a strong supporter of FDT, so I'm pleased to see that FDT über alles.
Yes.
Über alles, indeed.
Is really the essence of most non-equilibrium statistical mechanics. Everything is written there, as Jorge was pointing out. So, okay, I think that there are no more questions, and Marco agrees with me. We could thank again, warmly thank again, Jorge for his very nice seminar. We hope to see him present sometime in the future.
Maybe, who knows? Some sunny day.
Yes. Have a nice time to everybody.
Ciao.
Ciao, Jorge.
Ciao.
Grazie.